In our previous lesson, we talked about how pH is used as a measure of the relative concentration of hydronium. Well, there's another scale that we can also use, which is similar to pH, called pOH, or parts hydroxide. Sometimes it's more useful to use pOH versus pH because pOH measures the concentration of hydroxide specifically. You can see that the equation for pOH is similar to that of pH. It's the negative log base 10 of the concentration of OH minus instead of H3O plus. So the higher the pOH, the more acidic something is, and the lower the pOH, the more alkaline or the more basic that substance is. Strong bases completely ionize. They form a positively charged ion and the corresponding hydroxide. It's important to realize, though, when we're talking about a group 1 hydroxide that's acting as a strong base, the concentration of sodium plus 1 and OH minus 1 is going to be the same as the original base. If we have something that's a group 2 strong base, such as calcium hydroxide, however, one thing that we have to watch out when we're working with pOH is the fact that when we have 2 hydroxides per 1 formula unit of this compound, the concentration of Ca2 plus will match that of the original compound because it's a 1-to-1 ratio. However, the OH minus concentration will be twice that of the original compound if there are 2 of them in the chemical formula. So that's one little trick that we have to watch out for with group 2 strong bases. When we want to determine the pOH of a solution, such as this solution, which has an OH minus concentration of 6.3 times 10 to the negative 2nd molar, pOH says that it's equal to the negative log base 10 of the concentration of hydroxide. I simply substitute my number in for the concentration of hydroxide and allow my calculator to do the work for me. So the pOH of this solution is 1.20, which is fairly low. That means that this solution is very alkaline, not very acidic. Acidic substances have very high pOH values. It's the opposite of the pH scale. If we were to determine the OH concentration of a solution of potassium hydroxide in which we know it's pOH, we can use the same alternate form of the pOH equation as we did with the pH equation. pOH is equal to the negative log base 10 of the hydroxide ion concentration, and if I want to rearrange this equation, I can take the opposite of both sides and take the 10 to the power of both sides to get this new alternate form of the pOH equation. The concentration of hydroxide is equal to 10 to the negative pOH power. So from this point, all I have to do is substitute my pOH as the negative exponent of 10. And if I calculate my final answer, it comes out to be 1.7 times 10 to the negative 3 molar, which is pretty high. This is a fairly strong base, so this concentration makes sense because this is a strong base of potassium hydroxide. There's one other relationship that connects pH and pOH. This equation listed above, pH plus pOH is equal to 14, is extremely useful if we want to go back and forth between hydronium ion concentration and hydroxide ion concentration. Since these two numbers both have to add together to give us 14, we can use that to interchangeably go back and forth between the concentration of those two ions. Alternatively, we can also use the equilibrium constant of the dissociation of water, 1 times 10 to the negative 14th, is equal to the concentration of these two ions multiplied together. However, this equation, while it will work, does involve a little bit more algebra, so I'm going to stick with the pH plus pOH is equal to 14 equation in some of the examples that I work out. So this is a different situation because we're given the concentration HClO4 is perchloric acid. This is a strong acid. So we can certainly assume that this concentration here is equal to the concentration of H3O+, but we're trying to find the pOH, not the pH. So my plan of attack should be find the pH first, and then I can use the equation that we just reviewed here to go back and forth and find my pOH once I find the pH. So the very first thing that I need to do is I need to substitute the concentration of the strong acid into the pH equation. Negative log base 10 of the concentration of the perchloric acid is going to give me a pH of 1.82. That makes sense because this is a strong acid. Now that I've found the pH, I can simply use the relationship that both numbers together have to add up to give me 14. So therefore the pOH is simply 14 minus the pH that I just solved for, 1.82. So the pOH of this solution comes out to be 12.18. This is a strong base, calcium hydroxide. However, in this particular example, we have to keep in mind that calcium hydroxide has 2 hydroxide ions per 1 formula unit. Eventually, we can certainly find the H3O+ concentration, but that's going to involve us finding the pH. Since this is a strong base, it makes more sense for us to find the pOH first, and then maybe go from the pOH to the pH to find what we need to find by the end of the problem. The very first thing that I need to realize is that the concentration of hydroxide is actually double that of the original strong base, because this strong base has 2 hydroxide ions for every 1 formula unit, so the concentration of OH- is double. Now, to use this concentration to find pOH, now that I know the concentration of OH-, pOH is equal to the negative log base 10 of 0.2, and if I take that and calculate the pOH, it comes out to be 0.70. Now, pOH does not directly give me the concentration of H3O+, but I can use the relationship that we talked about earlier, that pH plus pOH equals 14, to very quickly find that the pH is equal to 14 minus 0.7, so the pH of this solution is 13.30. Checking to make sure that that answer makes sense. It does, because this is a strong base and I would expect its pH to be very high. Then we worked in a previous problem with the alternate form of the pH equation, and if I take the log base 10 of both sides and take the opposite, I can solve directly for the H3O+ concentration by taking 10 to the negative power of the pH. So if I take 10 to the negative 13.3 power, it comes out to be that my concentration of H3O+ is very small, 5.0 times 10 to the negative 14th molar. These are 3 practice problems that will help us kind of practice going back and forth between pH, pOH, and the concentration of either hydronium or hydroxide. Take a few minutes, pause the video, and try these problems yourself, and we'll go over the solutions here after you have a chance to work them out yourself. For number 1, to find the pOH of a solution in which you're given the pH, it turns into a simple situation where you just have to take the pH away from 14, and that should give us a pOH of 10.59. For number 2, we're starting with the pOH of the solution. To find the pH, I need to take 12.87 away from 14. That gives me the pH of the solution to be 1.13. And then we can use the alternate expression of the pH equation. H3O+ is equal to 10 to the negative pH power to calculate the final concentration of hydronium, which comes out to be 7.4 times 10 to the negative 2nd molar. For this final problem here, I have the hydroxide concentration. I want to know what the pH is. So to determine that, I can find the pOH from the OH- concentration. First, pOH is equal to the negative log base 10 of the concentration of hydroxide. That comes out to be 11.77. And then to get to the pH of this solution, I can take 14, subtract my pOH, and my pH becomes 2.23. That concludes our discussion of pOH and how it relates to pH. Our next lesson will center on the topic of how we look at conjugate acids and conjugate bases.